Hello, I welcome you all in this course on mechanical measurement systems. And today we will discuss about the pressure measurement, and we will discuss different type of pressure measuring devices. So, pressure measurement. Pressure measurement is a very important activity in any research organization or in any industry. Almost in all the industries, it is required that pressure be measured. And normally dial type of pressure gauges are used in the industries for the measurement of pressure, or pressure transducers are used. These transducers, if you go by input and output, the input to these transducers is pressure, and output we get in two forms, either 0 to 10 volt DC normally. It can be 0 to 5 volt DC also, or plus minus 5 volt DC also. And if the pressure has to be transmitted to a far off location, then normally current type of output is preferred, that is 4 to 20 milliamperes of output. But if we go by the process through which the pressure is, now this output from the transducer goes to the data acquisition system, and this output range is calibrated for input pressure range on a linear scale, and that is how the pressure measurement is done. Now in this cylinder or a box or entity, there are sensors and there is a lot of electronics which converts the pressure signals to the voltage or current signals. Now today we shall start with the basic measurement devices. And before we go to the pressure measuring devices, I will give you a slight idea about pressure measured in different units. The normal atmospheric pressure is 760 mm column of mercury, the pressure equivalent to 760 millimeter column of mercury, and in inch point system the atmospheric pressure is 14.696 psi, pounds per square inch. And when we express one atmospheric pressure in SI system, it becomes 101.3 kilopascal, right? When it is expressed in MKS system in kg per centimeter square, 1.033 kg per centimeter square. Now there is another unit of pressure is ATA, ATA, and 1 ATA is 1 kg per centimeter square. Now pressure is also expressed in terms of a millimeter column of water. So 1 millimeter of water is equal to rho GH. Let us take density 10 to power 3. G is 9.81 and height is 1 mm, so 10 to power minus 3, it is 9.81 Pascal. 1 mm of mercury also expresses the pressure, and 1 mm of mercury is 1 torr. It is written as 1 torr. Vacuum is, or very low absolute pressure is measured in terms of torr. Now 1 torr, this is also unit of pressure. So 1 torr is equal to 1 millimeter of mercury. So 1 millimeter of mercury is equivalent to relative density of the mercury is 13.6 into 10 to power 3. This is rho. G is 9.81. This is G into H is 1 into 10 to power minus 3. And if we take the product of this, we will get 133.3 pascals. Pascal is newtons per meter square. So very low pressure or the vacuum is often expressed in terms of millimeters of mercury or torr. Now, classification of pressure. The pressure is also expressed in terms of absolute pressure, gauge pressure, and vacuum. Suppose there is an absolute vacuum, the pressure is going to be zero because there are no molecules to transfer the momentum. So at zero, at absolute vacuum, there is no pressure. And then it is atmospheric pressure. This is atmospheric pressure. So atmospheric pressure may vary depending upon the location, temperature, and it is dependent on many factors. So where on the earth you are located, what is the temperature of that particular location and geographical condition, this atmospheric pressure is decided. And it varies, I mean, day-to-day basis. Even hourly variation is observed in atmospheric pressure, though it is very less, but it is also, when atmospheric pressure goes down significantly, then there is an inflow of the wind and storms takes place. So we will not discuss here about the weather conditions. Now this is atmospheric pressure, let us say for mean sea level, it's 101.3 kilopascal. And now above this pressure, the pressure measured above this pressure is gauge pressure. So normally the pressure indicated by the pressure gauge is the gauge pressure. If you want to make use of that pressure, we will have to add the atmospheric pressure. For example, steam is available at gauge pressure of 2 bar. It means the steam available at 2 bar plus atmospheric pressure, that is the absolute pressure of steam, and this pressure has to be taken into account while calculating the thermophysical properties or doing any calculations related with the steam. So whatever is indicated by the gauge, the atmospheric pressure has to be added, and this will give the absolute pressure. Now other term, this is absolute pressure, gauge pressure, vacuum. So pressure below the atmospheric pressure is known as vacuum. Suppose pressure below the atmospheric pressure is, let us say, 100 kilopascal. If there is a vacuum of 20 kilopascal, it means the pressure is 20 kilopascal below the atmospheric pressure, or absolute pressure is 80 kilopascal. There is a static pressure and dynamic pressure also while measuring the system. Static pressure is, suppose for example, in case of pitot tube, we have already used that, right? So pressure here from this column was coming static pressure and stagnation pressure due to stagnation effect of the velocity, because here the pressure P by rho, the total pressure is going to be P plus half rho V square. This will be the total pressure here, and this is known as stagnation pressure, or and this is static pressure, and difference of this will give the velocity head of the fluid. Now there are pressure measuring instruments which are used for different range of pressure measurement. For example, instruments for 1 mm of mercury to 1000 atmospheric pressure. The normal pressure gauges and transducers are used for this purpose, and they are sort of, they use Bourdon tubes or diaphragm type of gauges for the purpose of measurement. They are the sensing elements. When it is ultra high pressure, for ultra high pressure, we can go for Bourdon tubes, and resistance pressure gauges are used for ultra high pressure when the pressure exceeds 1,000 times of atmospheric pressure. When the pressure is below 1 millimeter of mercury, for below 1 millimeter of mercury, pitot tubes are, or the manometers are used. Manometers are used for the pressure measurement, and when the pressure is ultra low, then McLeod gauge and Pirani gauge and all are used for the pressure measurement. So we will start with the manometers, which is very simple and common device for pressure measurement. Manometer. In manometer, we'll start with, manometer is a device when the pressure is measured with the balance of vertical column of the fluid. Now the simplest one is piezometer. For example, there is a flow in a pipe. At one opening of pipe, you put a vertical transparent tube. The gauge pressure equivalent to the pressure inside the pipe will be compensated by the water column in this tube or liquid column in this tube. This is P atmospheric. So just we will add rho GH in P atmospheric, we will get the total pressure inside the tube. So P is equal to PA plus rho GH. But the piezometer cannot be used for the gases because gases do not have free surface. And the second drawback of this is it cannot be used in the case of vacuum. Vacuum cannot be measured with the help of piezometer. Another type of pressure measuring device is Utube Manometer, and which is very popular. In Utube Manometer, it is a U-tube normally filled with the mercury or any other fluid, right? So it is filled for mercury or with any other fluid. Suppose, and this side is connected to the pressure, where pressure has to be measured. This side is open for atmospheric air, and this head H. Now pressure at this plane is same on the U-tube. So if we take pressure at 1 and pressure at 2, so pressure at 2 is P atmospheric pressure plus rho mercury GH, and this side pressure plus rho the pressure of this column equivalent to H is rho F GH. Now if you want to have the gauge pressure, that is P minus PA, it is going to be P minus PA is going to be GH rho M minus rho F. Often when rho M is much greater than rho F, then often it is neglected also. And this is how we get the gauge pressure and absolute pressure in case of Utube manometer. Now Utube can also be used for differential pressure measurement, as we have seen in the case of venturimeter. Now differential manometer, right? So in differential manometer, so let us take case of a venturimeter. There is a Utube manometer, and both sides are not, any of the side is not exposed to the atmosphere. So pressure is exerted here and pressure is also exerted here, right? And then the difference in the column H will show the magnitude of pressure difference, and these type of calculations we have already done. So in differential pressure manometer, none of the side is exposed to the atmosphere. In fact, both sides are pressurized, and difference in the column the pressure, the level difference in the column speaks about the differential pressure, and this can be easily calculated by using the Bernoulli's equation. Now, there is another type of manometer which is known as well type of manometer. In well type of manometer, there is a well which is having a very high volume, and this side is connected to certain pressure or exerted by certain pressure. And this bottom of the well through a U-tube is connected to a transparent tube which has negligible cross section or very low cross section if we compare this with well. Now this well and the U-tube are filled with some fluid, let us say mercury, and because it is pressurized, some column has been developed. This is known as H. Because the volume of this fluid is not infinite, so in this process, the level of this mercury level or the fluid level in this will also go down, and that is, let us say the new acquired level is this, and this is H dash. Now we will do the pressure balance. Now for the purpose of pressure balance, now the pressure difference is this much, not H, but it is H plus H dash, right? So P plus rho F G H plus H dash. This is the equivalent column here, is equal to atmospheric pressure plus rho mg H plus H dash. Now we will not take here H, we will take H plus H dash. And now again P minus PA is going to be rho m minus rho f into G multiplied by H plus H dash. Again here, if we take the volume, then if cross section of area of this is A and the cross section of area of this is small a, then A multiplied by H dash is equal to A multiplied by H. Now here we will replace the H dash by this and we will get rho m minus rho f G 1 plus A by A H. Now if A is much larger than A, then we will neglect this and we will get rho m minus rho f GH. Now this is one case. If this, sometimes this height is not sufficient, suppose the height is 1 millimeter, 2 millimeter. In that case, in any of the manometer, the arm is inclined, right? And we get certain angle alpha, right? And this length L, alpha may be 10 degree or 20 degree. So that we can get sufficient length of column, this increases the accuracy of the measurement. And then we will take L sin alpha, this is the actual head. So this head H also can be replaced by L sin alpha if this arm is inclined, right? So this is the well type of manometer. And U-tube double reservoir manometer. We can have reservoir on this side also. Double reservoir manometer. These type of manometer are also there, right? So we can have several type of arrangements, but the fact remains we have to make use of Bernoulli's equation, right? And if there is a difference in elevation, sometimes there is a difference in elevation also. For example, the end view of one pipe is this, end view of another pipe is this, right? And then they are connected by the differential manometer, right? So for every case, now here H will also, this also will add to the head. So ultimately we have to make the pressure balance on both the legs of the manometer when pressure is same, and then we can measure the pressure above this side and pressure above this side, and we will balance that pressure. So this is the basic methodology for finding out the pressure or pressure difference using the manometers. Now, manometers are inexpensive and accuracy is also good, but they have poor response, or they are not used for the dynamic response of the system. They are very good for the static measurement. They are suitable for the low pressure. For high pressure, we cannot go. Suppose I have to measure absolute 1 bar or 1 bar gauge pressure with the help of a manometer, then I will have to go for 10.3 meter height of tube, which is difficult to handle, and it is fragile also. It is a glass tube. So fluids have to be compatible. Suppose fluids, they do react with each other, then the pressure gauge will not work. So both the fluids, that is the working fluid and the fluid of which the pressure is being measured, they have to be compatible. And the scope of error in the Utube manometer is, first is capillary effect. Certain height we get through capillary effect also. And another is reading in manometer. One should correctly read the meniscus of the height of the column, otherwise there are chances of error. And lastly, the gravity and temperature, they have also bearing on the measurement by the manometer. So they have to be taken into the account. Now, after the manometers, there are several gauges. And normally, for high pressures, we go for the pressure gauges. In pressure gauges, there is a dial, and there is an indicator, and this side is connected to any vessel or pressurized media, and when the pressure is exerted on the dial gauge, there is a deflection in the needle, and we get the output from the pressure gauge. But inside the pressure gauge, normally there is a Bourdon tube which gets expanded. I have already explained the working of the Bourdon tube in a pressure gauge, which causes the deflection of the needle, or it may be a diaphragm type of gauge. Suppose there is a pressure transducer. Like in a pressure transducer, physically if you look at, it is a small cylinder, maybe of the length of say 2 inches and diameter of ½ inch, right? So it is a cylinder, but inside it there is a diaphragm, and on the diaphragm, when the pressure is exerted, deflection of diaphragm takes place. And when we are able to measure the deflection in this diaphragm, we can convert this deflection into the electrical pulse. This diaphragm can be of dish type. This is dish type diaphragm. It can be a flat type of diaphragm. This is normally used for small size of pressure gauges. It can be a corrugated diaphragm, and it can be a capsule shape of diaphragm. It depends on the application and the size of the pressure gauges. The corrugated, especially corrugated diaphragm, is used to improve the performance of strain gauges. It is used for large size of strain gauges. And this corrugated, diaphragm also increase the linearity. When there is a deflection, the linearity between the load applied and the deflection. And it causes less stress, it is obvious, it causes less stress, but dynamic response of the corrugated diaphragm is not that good. Okay, so it is normally used where the static signals are there. It's corrugated type of diaphragms. But diaphragm and Bourdon tubes, they are two important primary sensing elements, and on the diaphragm you can put, for measuring the deflection, you can use several techniques. You can put a strain gauge on the diaphragm, right? The strains will be developed, or you can put a piezoelectric transducer on the diaphragm that will also convert the force signals into the electrical signals. So, but they also have limitations. The limitations is, first of all, diaphragm of the strain gauges have slow response, I have already stated. They also show certain order of hysteresis, and output is feeble, output is weak. So amplification of the output is also required in such type of diaphragm type of strain gauges. They are susceptible to the shock and the vibrations. So care has to be taken while installing these strain gauges that the place is free from shocks and the vibrations. Material for these strain gauges, so diaphragms is normally nickel, chromium or iron. And elastic limit of the foil is 560 megapascal, approximately let us say 500 megapascal. 560 or we can safely we can take 500 megapascal. For low pressure measurement, McLeod type of pressure gauge is used. It is very popular. Now in McLeod pressure gauge, there is a bulb right, and bulb has a tube and tube has two bifurcations. One is going this side, another is going to this side, and there is a vessel with filled some, let us say mercury, with some fluid like mercury. So mercury is filled here, mercury is also filled here, and this side, now this has a column, this side has a column, right? And this side is also having a column. This side is also having a column, and column has a bifurcation also. Arrangement is something like this, and here there is a temperature scale. Some scale is provided here, right? Now, this is also open. Now, this movable reservoir is lowered. When the movable reservoir is lowered, the pressure of the mercury or the fluid starts falling. Let us say. Right? And the fluid of which the pressure has to be measured start entering this tube. And we'll keep on lowering this movable reservoir. Movable reservoir. When it goes below this mercury goes below this point, the entire fluid will enter here. Right? When fluid enters here, we'll start raising this movable reservoir, and the fluid will start getting the compress. And it will come somewhere here, the pressure will increase. It is isothermal compression. So P1 V1 is equal to P2 V2, right? This will hold good here. So when it is compressed, then it is confined to this space. This volume is measured because we have a scale here. This volume can be easily measured. Cross-section area and the volumes are known to us. So, and we have pressure here also. The fluid is filled in this arm also. And due to pressure here, there is a differential in pressure which is denoted by H. Right? I am repeating. The fluid which is coming here enters in this ball, and when we lift the movable reservoir, this fluid starts getting compressed, the pressure keeps on increasing, and when again this point is regained, I mean the same level is regained by this movable reservoir, some pressure difference, because earlier there was no pressure, now there is a fluid in it, so pressure will be there. So there is going to be the difference in the levels, and this is shown by H. H is the height of the column here. So P into volume of the bulb, it is quite large, is equal to PCVC, volume of the capillary. Pressure into volume of the bulb is equal to pressure and the volume of the capillary. So first initial volume and the last volume. right? So we have equated them, and pressure in the capillary minus P is equal to Y. Okay, and P is this pressure. So final pressure minus initial pressure is Y. Now P, why I am writing Y? Why I am not writing YGH? I am not writing YGH because it is expressed in terms of column of mercury. So P is also expressed in column of mercury. It is not Pascal or kilopascal. So, and PC is also is equal to P VB by VC. Now using these two equations, we can find the value of P. P is equal to AY square divided by VB minus AY. If you manipulate these two equations, this is going to be the final expression. Right? Or if you want to neglect AY, because AY, if you compare the volume of the bulb, it is much larger than the volume of the capillary, then P is equal to AY square by VB. Now to have a clear understanding of the pressure measurement by McNeil gauge, let us try to solve this numerical, which states that a McNeil gauge has VB is equal to 100 meter cube. So volume of the bulb is volume of the bulb hundred centimeter cube. Volume of the bulb is 100 centimeter cube. So if a reading of 30 mm is there, so volume of the bulb is 100 centimeter cube. So volume of the capillary is going to be pi by 4 d square L is equal to pi by 4 into 1 square into 30 into 23.6 mm cube. Volume of the bulb is 10 to power 5 mm cube. Right? And then pressure is then 23.6 volume of the capillary VC multiplied by 30. 30, it is the height of the column. It is 30 mm, reading of 30 mm. So height of the column is 30 divided by VB. It is 10 to power 5 minus 23.6 volume of the capillary. Now, if you solve this, we will be getting the value of P as 0.0071 torr. So this we have got this P is equal to AY square divided by VB minus AY, or we can write AV capillary, AY is the volume of the capillary, so AY is volume of the capillary, and Y minus VB minus AY is also volume of the capillary. It can be written like this also. So we have used this here to find the value of P. And P is how much? 0.0071 torr. If we multiply this by rho g, this is torr. If we multiply this by 133.3, we will get pressure in kilopascal. And that pressure is in pascals. So the pressure is 0.94 pascal. Now if we neglect this, right? So we are getting two pressures. One is considering the capillary volume, another is neglecting the capillary volume. If we are considering the capillary volume, then we are getting 0.9464. And when we are neglecting the capillary volume, the pressure is 0.9438. If you want to find the error in the measurement is going to be 1 minus 0.9438 divided by 0.9464 multiplied by 100, and this will give 0.275% of error. So even if we neglect the volume of the capillary, the contribution of error is not very significant. That is all for today. Thank you very much. In the next class, we'll start with the force measurement and the torque measurement.